Hello everyone, I am Dr. Ramesh Panickar. I am an associate professor at the Department of Chemistry in Indian Institute of Technology, Kanpur. So in the last 3 lectures that I had given, I was talking about the chemistry of haloalkanes and haloarenes. So today I would continue to do that. So this, as you already know, is from the unit 10 of the NCERT textbook for chemistry for class 12 students. And what is left out of this unit to be discussed is about the reactions of haloarenes. So haloarenes, as you know, are compounds where halogen atom is attached to an aromatic compound. So in the last class we had discussed about the reactions of haloalkanes, and I also made it a point to mention that the reactivity pattern of haloalkanes are quite different from that of haloarenes. So we would look at the reactions of haloarenes today. In the reactions of haloalkanes, one of the most interesting and most useful reaction was the nucleophilic substitution reaction. We said that if we have a halogen atom attached to an alkyl group, the halogen atom can be replaced by a number of different functional groups by using various nucleophiles. So that was supposed to be, and that we have mentioned, is actually the most useful reaction and one of the best to make various derivatives of hydrocarbons. But now once we come to haloarenes, quite interestingly, all the nucleophilic substitution reactions at first seem to be a possibility. These reactions do not work well. So unlike alkyl halides, aryl halides are extremely slow and extremely sluggish when it comes to reaction with nucleophiles. So there are various reasons for this. So we would look at the reasons one by one. So if you would have a look at the screen here, you would find that one of the factors is a resonance effect. So as you can see, whenever we have a halogen atom attached to an aromatic ring, the halogen atom that I have shown here is chlorobenzene. So chlorine has lone pairs of electrons. So these lone pairs of electrons, because the chlorine carbon bond can rotate, these lone pairs of electrons would come parallel to the electron cloud that is present in an aromatic ring. So you know that an aromatic ring is stabilized by electron clouds on either side of it. So similarly, when a chlorine atom has this lone pairs of electrons, they can come in parallel with the electron clouds present on an aromatic ring and start to interact with these electron clouds. So they can have bonding interactions, which we normally say as resonance structures that can be formed from this, or the effect is called as resonance effect. So these representations show you how we would be able to draw them in simple chemical terms and show how a bonding interaction can happen between the lone pairs on chlorine and the aromatic ring. So this is what we mean by resonance effect. So you can see that the lone pair of the chlorine atom is donated to the chlorine carbon bond, effectively forming a double bonded compound. So that means we have a chlorine carbon double bond, but now that chlorine has given its electrons to form this bond, it receives a positive charge. But however, when the double bond is formed, one of the double bonds in the ring within the aromatic compound also migrates to the adjacent carbon, giving a negatively charged species. So from a neutral structure, we have a structure that is charged with positive charge on chlorine atom and negative charge on one of the carbon atoms. Now the negative charge does not stay on that particular carbon atom, it continues to move through the aromatic ring. So you would find that the negative charge then goes and forms a new double bond, while an existing double bond is now moved on to one of the carbon atoms to give you a new negatively charged carbon atom. Now this negatively charged then moves across the ring and forms a new double bond, and negative charge is localized on another carbon atom. So all these structures are written with the arrows that correspond to resonance structures. That means none of these structures really do exist. The actual structure is a mixture of all the structures that we have drawn here. So out of the 4 structures we have, 3 of them have a positively charged chlorine atom, and all such compounds do have a carbon chlorine double bond too. So therefore this double bond character between carbon and chlorine makes it difficult to cleave the carbon chlorine bond. So in effect, the carbon chlorine bond has become shorter, it has a double bonded character, so it is much stronger than a single carbon chlorine bond. And one interesting thing to note is that whenever we were writing haloalkanes, we always said that the carbon which is attached to the chlorine atom receives a slight positive charge, but whereas in the structures that we have now, you would find that chlorine is having a positive charge. It is because we have a double bond that is generated on chlorine at the expense of a lone pair of electrons that was present in chlorine. So, it has a double bond between carbon and chlorine. So, a partial double bond between carbon and chlorine that results in lesser reactivity of this molecule. That means it is difficult to substitute that particular chlorine from the carbon atom. Now going ahead, a second reason for this is the difference in hybridization of carbon atom in CX bond. So I have two structures here, one of them is an aryl halide, a haloarene, and another one is an alkyl halide. So if you look at the carbon that is bonded to the halogen atom, in a haloarene it is an sp2 hybridized carbon atom. So what do we exactly mean by an sp2 hybridized carbon atom is that the amount of S character on the orbital that is being used by carbon, or the atomic orbital that is used by carbon, is more. So whenever we increase the S character in an orbital, the orbital becomes more electronegative because S is the inner shell. So therefore you would find that the increased percentage of S character in the orbital makes this particular orbital more electronegative, or in other words, the carbon that is bonded to X in a haloarene is more electronegative than the carbon that is bonded to a halogen atom in a haloalkane. So therefore, because the carbon is now more electronegative, it does not allow the bond to be polarized as much as it is polarized in a haloalkane. Or in other words, the electron that you find between carbon and halogen is not moved too much towards chlorine. So the extent of polarization is less. The bond therefore happens to be shorter. So if you compare a chloroalkane and a chloroarene, generally it is found that the chloroarene has a shorter carbon chlorine bond in comparison with the chloroalkane. So this shorter bond also means that it is stronger, and this also can be attributed to the fact that the carbon chlorine bond has a double bond character, which we saw before. So because of these factors, it becomes difficult to cleave this bond. So that is the whole point. So if you want to do a substitution with a nucleophile, we would like to break the carbon chlorine bond, so that becomes difficult. Now then we can also think about the other mechanism that was possible for haloalkanes, which was SN1 substitution reactions, where we have to assume that the halogen leaves from the molecule and gives a positive charge to the carbon atom to which it is attached. This is difficult because the bond is not polarized, and even if we assume that under forcing conditions we were to force an SN1 reaction on a haloarene, you would find that the positive charge now has to rest on an orbital which is sp2 hybridized. So carbon uses a sp2 hybridized orbital to form the carbon chlorine bond. Now when the chlorine leaves with its electrons, the sp2 orbital is now empty, or therefore the carbon receives a positive charge, and that orbital, so the problem with having that positive charge is, although aromatic ring is electron rich, if my palm is to be supposed as the aromatic ring, you would find that the electron clouds are on either side of this. So you have electron clouds on top and bottom of the aromatic ring. Now the orbital that has the positive charge also lies along the plane of this, so it is in one plane. So whenever we generate a positive charge is generated on the aromatic ring, that particular orbital is in the plane of the aromatic ring, and therefore that empty orbital cannot be supported by the electron clouds on either side, because this is actually in the node between the two components of the electron cloud that is available on aromatic ring. So this cannot be resonance stabilized. So that is the trouble we have. So therefore this aryl cations are extremely unstable. So there are two reasons. One of them, the empty orbital is now an sp2 orbital, which is more electronegative. So the carbon starts to feel more positive charge. And the second reason is that this particular positive charge or the absence of electrons cannot be supported by the electron cloud that is present in the aromatic ring, because it kind of falls in the nodes of this electron cloud, the node of this electron cloud. So that makes an SN1 mechanism practically impossible for haloarenes. So we have seen that the SN2 reaction required that we cleave the carbon halogen bond when the nucleophile approaches, and the SN1 reaction requires that it cleaves even before. So both these are not possible, and there is also another reason why SN2 reactions are not possible, because aromatic rings are electron rich. They have the aromatic electron cloud. A nucleophile is also electron rich. So when two electron rich species have to come together for a reaction to happen, you normally find that there is a large amount of repulsion between the electron rich species, and that results in the reaction being slower. So these factors, these 4 factors that I have discussed now, there is resonance, the difference in hybridization, instability of aryl cations, and finally the repulsion between a nucleophile and an aromatic ring. So all these factors contribute together and make nucleophilic substitution reactions of aromatic compounds extremely difficult. It does not mean that we cannot carry out these reactions. We can of course do these reactions, but some of these reactions would require extremely hard conditions in comparison with what was required for the reactions of haloalkanes. So I have an example here. So these are reactions of chloroarenes with hydroxide ions. So hydroxide ion is a nucleophile. So let us take the first example that is given here. So if you take chlorobenzene and treat it with sodium hydroxide, then the condition that is required is 623 Kelvin. So it is approximately 350 degrees Celsius and 300 atmosphere. So the reaction requires extremely high pressure and very high temperature. Only then the nucleophilic substitution does happen. So the nucleophilic substitution of a chlorine with a hydroxide anion is possible, provided we give extremely harsh conditions, including very high temperature and very high pressure. Now you can see that there are 2 steps to the reaction. One is where you treat it with sodium hydroxide at the temperature and pressure that I mentioned, and in the second step the same molecule is treated with an acid. So H plus here is required because under basic condition the phenol that is formed would be a phenoxide anion, because phenol is acidic. So in the presence of sodium hydroxide, after the first step the product you get will be a sodium salt of phenol. So you have to neutralize it, that is why we have H plus as a second step. Okay. Now in the second reaction what you are seeing is we have the same substrate, but we have added an NO2 on para position to the chlorine. So when we add an NO2 to the para position, this is a monosubstituted chlorobenzene or a chloronitrobenzene. So in this particular case we have this nitro group present, and then there is a dramatic difference in the conditions that are required. Earlier we needed a much higher temperature and very high pressure. Here the pressure factor is been removed, so this reaction happens at atmospheric pressure and at not so high temperature. So 443 Kelvin, approximately 175 degrees Celsius. So the reaction would happen at a slightly lower temperature than what was earlier required, and it gives us the product after a protonation using an acid. Okay. Now in the third example we have added one more nitro group, and we see that the trend continues. So as we keep on increasing the number of nitro groups in the aromatic ring, the reaction conditions become milder and milder. So under these conditions you need less than 100 degrees Celsius for the reaction to be carried out, and there is no requirement of higher pressure. So we get the product which is a dinitro phenol as the product in this case. Trinitrochlorobenzene. So here there are 3 nitro groups on the 2 ortho position and the para position. So if you would like to name it the other ways, we can say that this is 2, 4 and 6 positions of the chlorobenzene. We have nitro substitutions. But now you would find that the condition is extremely simple, and this reaction works almost like the reactions of alkyl halides. Here all you need to do is take water and warm the reaction mixture. So we do not even need sodium hydroxide where an OH minus nucleophile has to react. Instead, water with its lone pairs will be able to do a nucleophilic substitution reaction on this substrate and give us this product, which is picric acid. This particular product is called picric acid. Now, so what we have seen is that chloroarenes are sluggish. They do not give you nucleophilic substitution reactions. You have to really force the conditions. But as we keep on adding a group such as nitro, so nitro specifically here because nitro is an electron withdrawing group. So what we are actually doing to the substrates here by increasing the number of nitro groups is to make the aromatic ring electron deficient. So the aromatic ring was earlier electron rich. So once you put a nitro group, the nitro group is pulls the electron towards itself. So therefore the aromatic ring slowly starts to become electron deficient, and that would make the approach of the nucleophile to the aromatic ring easier, and also the aromatic ring would be able to handle a negative charge. So we would look at the mechanism soon, and then we will find how this reaction works. So, so in this page you can see the mechanism of this particular reaction. So what I have first here is the para-nitrochlorobenzene. So or para-chloronitrobenzene as it has to be called. So you would find that in the para-substituted compound, the reaction follows a very interesting path. It is not like SN1 or SN2 reactions. The OH minus starts to attack on the carbon atom that is attached to chlorine, and then we get an intermediate where there is a carbon atom that is attached both to chlorine and to the hydroxide group. Now the double bond that was present with that carbon atom has moved on to the adjacent carbon with forming a negatively charged carbon there. So there is a carbanion formed, and we have a carbon that is tetrahedral that is attached to 4 different groups. Okay. And now what happens, the negative charge is then delocalized throughout the ring, similar to the resonance structures that we drew earlier. So the negative charge moves on, and then a new double bond is formed, and then now we have the carbanion on the carbon that is attached to nitro group, and then it moves further and the carbanion reaches here, and finally when the double bond is reinstated, the chlorine atom can come out as a chloride anion. So effectively if you look at the structure on extreme left and the structures on extreme right, you see that this is a nucleophilic substitution reaction. The chlorine atom has been replaced by the hydroxide ion. But however, there are these intermediates, and these intermediates are called as Meitzenheimer complexes. So these intermediates that are written here are called as Meitzenheimer complexes. So these are compounds where we have a nucleophile added onto an aromatic ring by giving a negative charge on the aromatic ring. Now our aromatic ring in this case is substituted. We have substituted it with a nitro group. So you also see that nitro group is electron withdrawing, and in at least one of the structures, one of the 3 structures that I have written in square brackets here, you can see that the negative charge is on the carbon atom that is attached to the nitro group. So that means this negative charge also can be delocalized onto the nitro group. So therefore the nitro group, which is electron withdrawing, will be able to pull the electrons towards itself and stabilize the Meitzenheimer complex. So a Meitzenheimer complex is when a nucleophile adds on to an adds on to a haloarene and forms a negatively charged species along with a tetrahedral carbon atom. And now such species are stabilized whenever there are electron withdrawing groups present on the carbon atoms where the negative charge starts to appear. So there are 3 structures that represent the Meitzenheimer complex, and in one of them the negative charge is on the carbon atom that is attached to nitro group. So that makes this reaction happen. Now the first step of the reaction, where the OH minus has to come and start forming the tetrahedral carbon atom, this is the slower step in the reaction. It is reasonable because now we are talking about breaking the aromaticity of the aromatic ring. So here we had an aromatic ring very much intact. Now once we start forming this tetrahedral carbon atom, here the aromaticity of the molecule is lost. So this is therefore a very slow process. But once this has happened, the elimination of chloride as an anion is extremely fast. So the last step, that means breakdown of the Meitzenheimer complex into the products, is faster. So the first step is slower, whereas the second step is faster. So that is how this reaction works. Now I have the same mechanism for a orthonitro derivative. So that means I have orthochloronitrobenzene. So now in this particular structure, you would particular compound, you will find that it is the exact same things that are happening. The OH minus attacks, it forms a tetrahedral carbon atom. The negative charge is now already on the carbon atom that is attached to nitro. So very good. So the negative charge can be delocalized onto the nitro group and stabilized. Now the resonance structures continue to form. That means the negative charge continues to move through the aromatic ring, and we can again draw 3 Meitner-Heimer complex structures, all of them in resonance. So effectively the negative charge is centered through the 5 carbon atoms that are present in this complex, and only one of the carbon atom is tetrahedral in structure. So one way of drawing Meitner-Heimer complexes that you would find being used by people is to draw the structure like this with a negative charge and then a chloride, OH, and at nitro at whichever position you would like to put it, either ortho or para. So there is this negative charge that is delocalized through this part of the molecule, and we have a tetrahedral carbon there. So this is how normally a Meitner-Heimer complex is represented with a single structure. Otherwise we will have to draw all the 3 structures to represent it correctly. Now here again the first step is elimination of this. So in these 2 structures, these 2 examples that I have drawn, I have the nitro group on ortho and para positions, and in both the Meitner-Heimer complexes those are formed, you find that the negative charge is on a carbon atom that is near to the nitro, that is attached to the nitro group. So in the second case it is on carbon number 2, and in the first case it is on carbon number 4. So these structures are something that we need to remember, because those are the ones which make this reaction faster. Now I would go on and see what happens when the nitro group is on meta position. So that means when we have metachloronitrobenzene, here again the OH minus can come and attack here. So when OH minus attacks, we generate a negative charge, like just like in the other cases we do have the Meitner-Heimer complex, and now the negative charge forms a new double bond, and the negative charge moves through the ring by forming a new double bond and moving the electron, moving the pair of electrons through the aromatic ring. We get the second structure and finally the third. Now in this sequence of reaction, in this series of Meitner-Heimer complex structures that we have drawn, you would find that the negative charge is never on the carbon atom that is attached to the nitro group. So in this it is not on the carbon that is attached to nitro group, here again it is not the case, and not even in this. So therefore although nitro group is something that can withdraw electrons, it can stabilize the negative charge better if the negative charge comes on the carbon atom to which the nitro group is attached. Now if at none of the structures the negative charge comes to the carbon atom to which nitro group is attached, then the negative charge is not stabilized. So therefore a substitution of an electron withdrawing group such as the nitro group on meta position does not make this reaction faster. Once again we saw that chlorobenzene reacts very slowly to nucleophilic substitution reactions. We saw that if we increase the number of nitro groups on ortho and para positions, the rate of the reaction increases, the conditions required to carry out the reaction becomes milder and milder. However, if the nitro group is present on a meta position, this does not happen. So in short, we would be able to say that the rate of these reactions are enhanced only if the electron withdrawing group such as the nitro group is present on ortho and para positions, and if they are present on meta positions, then the reactions do not happen faster. Okay. So that is about nucleophilic substitution reactions of haloarenes. So you would already realize that it is a tough reaction to do, so people not normally go for that. But however, aromatic rings, because of its electron cloud, because of its rich electronic species those are present, the aromatic ring itself, they tend to give you another reaction which alkyl halides cannot give, and those are electrophilic substitution reactions. You have already learned them probably while you are learning aromatic compounds. So electrophilic substitution reactions do happen in haloarenes. Now what does a halogen atom do to an aromatic ring? So we are now going to discuss about haloarenes, that means these are aromatic rings that are attached to a halogen atom. So let us see what can a halogen do to an aromatic ring. So halogen atom by itself is something that will pull electrons out, because the carbon chlorine bond, the carbon halogen bond, the halogen pulls electrons. So they are slightly deactivating, so they tend to deactivate the aromatic ring. By deactivation of an aromatic ring, we mean that an aromatic ring loses its electron density to a substituent. So the substituent is something that pulls electrons slightly from the aromatic ring and make the aromatic ring feel less electron rich. So halogens do that. But however, halogen atoms also have these lone pairs. So these are structures we already drew once. So these lone pairs of electrons in halogen atoms can be delocalized onto the rings to get these structures. So it can go with a negative charge on ortho position, para position, and on the other ortho position, and in such structures we have this carbon halogen double bond. So this is something we saw, and the halogen gets a positive charge too. So there are two things now. One of them is the halogen atom pulls electrons from the aromatic ring because it is an electron negative atom. So therefore the aromatic ring is now electron deficient. At the same time, although it makes the aromatic ring electron deficient, whatever electron density is available on the aromatic ring, it is enhanced on ortho and para positions, because in these resonance structures you can see that there are negative charges which are on in structure 1 and 3, you will find that the negative charges are on ortho position to the halogen atom, and in structure 2, which I am showing you now, the negative charge is on the carbon atom 4. So therefore these structures are favor substitutions on these positions. So if at all an electrophile, so once again electrophiles are those species which have a positive charge or those which are electron deficient and are looking for an electron rich species to react with. So when an electrophile approaches a haloarene, it sees that the haloarene is not so easily reacting, but however if it has to react, it would try to react through ortho and para positions of the halogen atom. It is because those are the ones that have negative charges in the resonance structures. So here I have these structures representing an ortho attack and a para attack, that means attack at an ortho position and at a para position. So simply drawing, we would be able to draw that the double bond present in the aromatic ring would migrate to react with the electrophile, which is shown as E and which is shown as E having a positive charge. Then a new bond is formed. Of course this carbon atom has a hydrogen atom, so we say that this carbon is now a tetrahedral, and the positive charge resides on the carbon atom that has chlorine. Now the presence of a positive charge adjacent to chlorine atom is not good, because chlorine is electronegative, so it does not want the positive charge there. So therefore the ring, that is why we say the ring is deactivated. But however, once the positive charge comes there, the lone pairs can stabilize the positive charge. So that also helps in the ortho attack. So if the attack has to happen, it can happen in ortho. Similarly, if the attack has to happen in para position, we have a new carbon E bond where E is the electrophile, and that carbon now is tetrahedral, and if you draw two arrows as I have shown here, you will be able to see that the positive charge is now on the carbon that is attached to chlorine, and chlorine will be able to stabilize the positive charge using its lone pair. So these are the reasons why ortho and para positions, substitutions at ortho and para positions can be stabilized by halogen, whereas if the substitution was at meta position, the positive charge will not come on to the carbon having chlorine, and therefore a resonance stabilization will not be possible. So you can draw those structures yourself and feel for it. Okay. So now let us look at some of the most useful electrophilic substitution reactions of haloarenes. So the first reaction is halogenation itself. So that means if we have a haloarene, we can add more halogen atoms to that. So this is a reaction we have learned while we are talking about the preparative methods for haloarenes. So you can take a haloarene, treat it with another halogen molecule, either chlorine or bromine, in the presence of anhydrous FeCl3 or Fe itself, so which would form FeCl3, which acts as a Lewis acid, and FeCl3 would then react with chlorine, forming what will be FeCl4 minus plus Cl positive. So the Cl positive that is formed would be the electrophile. So if you look at the reactions of that electrophile that I mentioned earlier, where the electrophile is shown as shown in red color, here that electrophile is Cl plus. Now Cl, the electrophile thus formed, would then react on ortho and para positions as expected, and normally you would also find that the substitution on para position is more favored. It is just because two substitutions on ortho positions, that means 1,2 substitutions on aromatic ring, as in this case. So you can see here 1,2 dichlorobenzene. So when you have substitutions on adjacent carbon atoms on an aromatic ring, there would be some steric hindrance, because if you look at this double bond is now as if it is a cis double bond with both the chlorine atoms are on same side. So it is like a double bond having cis substitution, so they are very close, so there would be some sort of repulsion between them. So normally you would find that the para substitutions are favored in electrophilic substitution reaction. So halogenation gives you two products, a mixture of ortho and para substituted compound, 1,4-dichlorobenzene and 1,2-dichlorobenzene, or so out of these two dichlorobenzenes, one which has the substitutions on 1 and 4 position, that is the para positions, will be the one that is formed as the major product. Okay. So the second reaction we will talk about is nitration reaction. So nitration reaction is by which we put a nitro group onto the aromatic ring, and normally depending on the electron richness of the aromatic compound that is subjected to nitration, we can use various reagents. So in this case you see that we use a reagent that is HNO3, nitric acid and sulfuric acid. A mixture of nitric acid and sulfuric acid is sometimes called as a nitrating mixture. So, this particular mixture will be able to nitrate a molecule, because under these conditions HNO3 gets protonated and we would generate an electrophile which is NO2 positive. So, this is the electrophile that is reacting, and this electrophile can then go on to ortho position or para position, forming two different mono nitro compounds. So, 1-chloro-4-nitrobenzene and 1-chloro-2-nitrobenzene. So, these are the two compounds that we would get. And if you have to say which is the major compound, of course the major compound is the one where substitution is at the 4th position. We have already seen why. So this is also a useful reaction of haloarenes. Now the third reaction is sulfonation. So in sulfonation what we add is an SO3H group. So it is called sulfonic acid group. So if you take a haloarene and treat with concentrated H2SO4. So concentrated H2SO4, there again what happens is the one H2SO4 molecule will protonate another H2SO4 molecules and a water molecule leaves, and effectively we get an electrophile which can be written like this. So SO3H is the electrophile in these cases. So then SO3H would react with the haloarene both in ortho and para positions. We would get two products, that is 4-chlorobenzene sulfonic acid and 2-chlorobenzene sulfonic acid, and out of these two structures you already know that the 4-chlorobenzene sulfonic acid would be the major product and 2-chlorobenzene sulfonic acid would be the minor compound. Okay. So the next reaction that we will discuss is Friedel-Crafts alkylation. You have already learned Friedel-Crafts alkylation of aromatic compounds. So in this what is required is a haloalkane. So we take a haloalkane and treat it with anhydrous AlCl3, aluminum chloride, where aluminum chloride acts as a Lewis acid and breaks the carbon CH3Cl bond. So effectively what we would have is something that can be represented as CH3 positive, especially if the alkyl halide used is methyl chloride, then we do not really make a CH3 positive, but we would have something that is partially bonded to chlorine and having a lot of positive charge on CH3. So this again then gets bonded to aluminum. So this is how we polarize this molecule and negative charge starts to develop on chlorine. So we have an electrophile that is now an alkyl cation, a carbocation, and that electrophile would react with the haloalkane on ortho and para positions and giving us 1-chloro-4-methylbenzene and 1-chloro-2-methylbenzene. The 2 substituted product, the ortho substituted product is the minor product. This reaction has an interesting fact that once we add an alkyl group onto a benzene ring, onto an aromatic ring, the alkyl group makes the benzene ring more electron rich. So there is only one problem with this reaction. Normally when we carry out this reaction, the products that are formed in the reaction are more electron rich, are more activated than the starting materials themselves. So they might start giving you multiple alkylation. So the reaction may not stop at forming one CH3, we might end up getting additional CH3 groups on the aromatic ring. So this is one of the problems with Friedel-Crafts alkylation, because the product always is more reactive than the starting material. So that is something that we need to keep in our mind whenever we want to do a Friedel-Crafts alkylation. There are other problems with the reaction too, which you might learn if you take up chemistry in the higher class. Okay. Now Friedel-Crafts acylation is another reaction where instead of an alkyl halide we use an acyl halide. So these are acid chlorides. So what I have here is acetyl chloride, so we can call it as Friedel-Crafts acetylation in this particular example. So if you take acetyl halide, this also has a carbon chlorine bond and we use the same catalyst. So the catalyst we use is anhydrous aluminum chloride. Now what would aluminum chloride do? Aluminum chloride would break the bond here and then we get CH3CO as the electrophile. So you would find that CH3CO with a positive charge on carbon, which would also be shared with oxygen. This is a relatively stable electrophile, quite unlike methyl cation. So this acyl cation would now be able to act as an electrophile and react with the aromatic ring, giving us two products, two mono-substituted products, one where the substitution is in 4th position, another one where the substitution is in 2nd position. Of course, the major product is one where the substitution is in the 4th or para position. Now, unlike alkylation reactions, acylation reactions would stop at mono substitution because the acyl group because the product that is formed in this case is a ketone. And once you have a CH3CO attached to benzene, it is called acetophenone. You will learn that while you study ketones. So, these compounds are more deactivated than haloarenes by themselves. So, because an acetyl group, an acyl group normally deactivates the aromatic ring. So, therefore, the action would stop at one step. So, in that way they would give you better control over an alkylation reaction. In both the cases, aluminum chloride is the Lewis acid that is most commonly used. There is only one issue. Normally in Prabha alkylation reactions you would only need to use one equivalent of aluminum chloride as the Lewis acid, whereas in this you would only required to use aluminum chloride in catalytic amount, because that is a catalyst that will continue to activate methyl chloride or the haloalkane that is used. But whereas whenever we do acylation reactions, the product has a keto group which coordinates with aluminum chloride. So, therefore, in these reactions the amount of catalyst used is more. So, you would have to use at least one equivalent of the catalyst for this reaction to go well. Okay. So, that is about the electrophilic substitution reactions of aromatic compounds. Now, we would go ahead with the third kind of reaction, that is reaction with metals. So, this is probably one reaction where haloarenes exactly match haloalkanes. So, the reactivity pattern is not largely different, because in these reactions the halo compound is reacting with a metal, and metals are substantially more electropositive than carbon itself. So, they have similar pattern of reacting between haloalkanes and haloarenes. So, one of the reactions called as the Wurtz-Fittig reaction. In this reaction we can take a haloarene and a haloalkane and treat with sodium and get these compounds which are cross coupled products where an alkyl group is now attached to an aryl. So, we get an R aryl, so an alkyl aryl compound, sometimes called as aralkyl compounds. So, this can be prepared once there is a cross coupling. Of course, there are troubles with this reaction. As you can see, we could assume that two R groups can combine and give you a hydrocarbon, give you an alkyl, give you an alkane. Similarly, two aromatic compounds can combine together, give you two aromatic rings linked with each other through a single bond. So, that is possible, and that reaction is called as Fittig reaction. So, in Fittig reaction what happens is two haloalkanes react together in the presence of sodium. Two molecules of sodium halide comes out, and then we get a compound where two aromatic rings are linked together through a single bond. These kind of compounds are called biaryls, and in this particular example we have two phenyl rings which are linked together, and this is called a biphenyl. So, we can prepare biphenyl by using this reaction, but it is you would normally feel that the synthetic utility is not much, because we are using metallic sodium for this reaction. So, metallic sodium is very reactive and it would normally catch fire if you are not careful and so on. It reacts violently with water, moisture. So, therefore, the moisture in the air is sufficient to give you a very explosive reaction. So, therefore, this is practically not used much, but we have to realize that this is a theoretical possibility. So, this is something that we can do. While studying the reactions of alkyl halides with metals, you have studied Wurtz reaction. So, Wurtz reaction was when an alkyl halide is treated with sodium to get a dialkyl compound, dialkyl hydrocarbon. Now, once you do the same reaction with haloarenes, we call it Fittig. So, that is why this reaction, where it is actually a mixture of Fittig reaction and Wurtz reaction. So, that is why it is called Wurtz-Fittig reaction. So, the name would make sense to you if you start looking at this compound. So, this is pretty much about the reactions of haloarenes. So, now we have discussed all the three kinds of reactions that haloarenes can give you. So, the reactions of haloarenes are electrophilic substitution reactions, which are probably the most useful. Nucleophilic substitution reactions through Meitzenheimer complexes, not so much useful, but it does happen. And finally, the reaction with metals, where there is a where we can do this coupling reactions, either Fittig reaction or Wurtz-Fittig reaction. So, in the last part of this chapter, what we would discuss is about some polyhalogen compounds that are most commonly found and most commonly used. So, the first member, so these are polyhalogen compounds, that means these are compounds where at least two halogen atoms are attached to the carbon atom. So, the simplest member is that you would come across is dichloromethane. So dichloromethane is a liquid. So if you take it at room temperature, it has a boiling point around 40 degrees. So it is a liquid but volatile liquid. So if you keep it, it just vanishes. And it is normally used as a solvent in organic chemistry labs wherever people use it. It is used as a solvent in industry. It can be used as a paint remover because most of the paints are organic compounds, and because dichloromethane is a solvent for organic compounds, it can be used to remove those. And because it is volatile, it vaporizes faster, so it can also be used as a propellant in aerosol. So now, however, it is not a nice compound to meddle around with because it harms. So if you inhale, and see, it has a low boiling point, so if you keep a bottle of dichloromethane open in this room, after some time you would have dichloromethane fumes in the room, and it harms the human central nervous system. So therefore it is not good if you are subjected to this compound. And one other thing is that whenever we use them in labs, if it happens to fall on your body, in the hand especially, and this part of the skin that is more sensitive, like between your fingers for example and between the nails and so on, you would immediately start to feel an extremely burning sensation. So dichloromethane has this problem. So it probably absorbs through the skin too. So if it touches your skin, on especially on sensitive skin, it would start to give you a very burning sensation. So these are things that we should be careful when we deal with dichloromethane. But however, its applications are so good, it is a very good solvent that it is still being continuously used, especially in organic chemistry laboratories. Now the next compound is trichloromethane, which you would all know more as a chloroform. Now chloroform again is a solvent. It is a very good solvent for fats. All sorts of fats can be dissolved in it. It is used as a solvent for alkaloids. So you know, alkaloids are compounds that contain nitrogen atoms. So these are natural products which are available in nature. So whenever we would like to extract them from natural sources, so imagine that there is a biologically active compound present in a plant material, and if you would like to extract it, chloroform is one of the solvents that you can use to extract out alkaloids. It also dissolves iodine, bromine and so on. Now it is also used for the production of freon, a refrigerant freon R22. So R22 is the compound that is attached to CH. So the compound it is a fluoro. So freons are all, we will talk about them. Freons are all compounds that have fluorine and chlorine attached to the same carbon atom. Now if you take methane, add 2 fluorine, 1 chlorine and 1 hydrogen, then that compound is called as R22. So this is made from chloroform. So that is one of its application. It has an anesthetic effect. So if you inhale it, you would feel dizzy. So it has an anesthetic effect. So just like dichloromethane, it is harmful. So we cannot inhale it too much. If you inhale them in smaller amounts, we will start to feel dizzy. So it has an anesthetic effect. And what is more damaging is if you get continuously, if you inhale a lot of it, it can damage our liver and kidney. So because in the liver, chloroform starts to get processed. So liver takes care of all these bad compounds that get into your body. So it will start to process chloroform and start to generate phosgene in liver, and all these byproducts that are formed, they can also harm your kidney. So chloroform is not something that we should be inhaling. It is also oxidized by air in the presence of light. So if there is light present, so you know these carbon chlorine bonds can break, because we have seen that before, that carbon chlorine bonds are weak, so sometimes they get broken if energy is provided in the form of light. So if there is oxygen and air present, then chloroform would break down into a compound that is called phosgene. So I would shown the structure of phosgene here. So chloroform would break down into phosgene, and phosgene is an extremely toxic compound. So if you inhale toxic phosgene, death is a sure thing if you inhale them in larger amounts. So chloroform itself is harmful, but phosgene is toxic by itself. It is just not harmful, it is toxic. But it has a nice smell. It has a smell that is similar to the fruit sapota, if you know, or chiku, that is called in Hindi. So this has a very pleasant smell, but it is an extremely toxic compound. So we should be very careful while handling chloroform. So therefore chloroform is not normally kept in a bottle half filled, because if you take a bottle and fill chloroform to the half, the remaining half is air. So now if this is exposed to light, then phosgene generates, and phosgene is a gas. So therefore whoever opens the bottle would actually get exposed to phosgene. So therefore normally chloroform is always kept in dark colored bottles, and as much as possible we fill it to the top so that there is no air present to react with chloroform. Now the third compound I will talk about is triiodomethane. So this is similar to chloroform. The chlorine is replaced with iodine, so it is CHI3. Iodoform was earlier used as a source of iodine. So and iodine is known to have very good effect because it can kill a lot of microorganisms. So it is used for healing wounds and so on. So it was used as an antiseptic. The reason why it was being used, even without knowing, people used to apply iodoform, and iodoform when exposed generates iodine. So it was actually iodine that was acting as the antiseptic. So when later on realizing that it is just iodine that is doing it, now iodoform is replaced with other compounds, but earlier it was used as an antiseptic. Now the next compound we will talk about is tetrachloromethane, CCl4, or carbon tetrachloride, carbon attached to 4 chlorine atoms. This is used for the preparation of a lot of refrigerants, and because it can be used for making freons that I have already talked to you about, and they can also be used as propellants. It has a boiling point of around 75, so it can be used and it gives you vapors. Now the problem with carbon tetrachloride is it is not advisable to use them, not even as much as chloroform or dichloromethane, because it is known to cause damage to nerve cells, and it can also cause liver cancer in humans. So it might cause, depending on the level of exposure, it may cause liver cancer. So therefore carbon tetrachloride we have to be extremely careful with. And another problem is carbon tetrachloride, if it is released into the atmosphere, it just moves up and reaches to the top and interacts with the ozone layer, and then it depletes the ozone layer through a free radical reaction where the carbon chlorine bond breaks and the radical formed would start to react with the ozone, thereby depleting ozone and thus causing problem. Okay. Now so far we have been saying that chloroform and carbon tetrachloride can be used for making freons. So these freons are, as I have told you once, they are compounds that are linked to fluorine and chlorine. So they can also be called as chlorofluorocarbon compounds. So these are compounds where a carbon atom is attached to chlorine and fluorine and maybe additional carbon-carbon bonds. They are stable. These compounds are extremely stable. They are unreactive, they do not normally react, they are non-corrosive, they do not cause any corrosion by themselves, and they are gases, but they can easily be liquefied because they are high density gases, so they can be liquefied by applying pressure. Now Freon 12 or CCl2F2 is one of the most used in industries, and it is prepared by from carbon tetrachloride using Schwarz reaction. So Schwarz reaction is something we learned. We learned that whenever we have to make a fluoroalkyne, we take a chloroalkane or a bromoalkane and treat with silver fluoride or cobalt fluoride and so on, certain metal fluorides, which would then precipitate a metal chloride or a metal bromide and form these carbon fluorine bonds. So the Schwarz reaction is used for making freons from compounds that have carbon chlorine bonds. Now they again are used as aerosol propellants, refrigerants, and for air conditions and so on. Freons, just like carbon tetrachloride, are one of the major causes of the depletion of ozone layer, because freons would again move up the atmosphere, reach where the ozone layer is, and then in the ozone once it reaches there, it would start to react with ozone through free radicals that are generated from these freons, and therefore deplete the ozone layer, which would result in ultraviolet radiations coming through the atmosphere into earth and would affect all the living organisms, because we cannot be exposed to ultraviolet radiations. So this is one of the disadvantages of using freons. So no matter how carefully we use freons, at some point of time they are going to be released into the atmosphere, and finally they are going to result in the depletion of ozone layer. So this is something that we should take care and try to avoid the use of freons with other refrigerants, for example, where the use of these harmful chemicals can be avoided. The last compound, last polyhalogen compound that I would talk about is probably the most talked about among all the polyhalogen compounds. This is DDT. So the structure of DDT is given here. So you can see the structure of DDT in this slide. So this has a trichloromethyl group and there is a CH, there is another carbon. So this is trichloroethane and the second carbon atom is attached to two benzene rings which are substituted with chlorine atom. So one of the ways of naming it is PP prime, that means para prime dichlorophenyl trichloroethane. So we have chlorophenyl groups, two of them. So that is why we say dichlorophenyl and then trichloroethane. So this part of the molecule is trichloroethyl part. So this is DDT. So DDT was known for a long time, but in the 1930s there was a scientist called Paul Hermann Muller who found out that this particular compound can kill a lot of insects. It can kill a number of arthropods. So suddenly this started to be used as an insecticide. It was started to be used as a pesticide in agriculture, in households people started to use this and so on. And this discovery was so important at that point because there were various diseases that were spreading through the human population by way of insects. So it included diseases like malaria, which is spread by mosquitoes. So that is one of the examples. So in order to prevent the spread of these diseases, people started to use DDT in larger amounts and started spreading them. So it was at that time such a find, it was such a useful compound that Muller got Nobel Prize in 1948 for finding the application of DDT. So it was talked about so much and its use was so much that people started to use it. But there was a problem associated with DDT, that DDT once it goes into the environment, it does not get disintegrated. So therefore what happens is once it is sprayed in a field, in an agricultural field or something, it just gets washed down into the water bodies and every fish and other animals that are living in the water body would start to consume compounds or get affected by DDT, or they will go into the body of these animals from water. And after some time these fish will be consumed by bigger animals such as birds for example, and then DDT gets into the body of birds. So a bird will be consuming very large number of fishes, and because DDT does not get out of the body or does not get disintegrated, therefore the amount of DDT present in the animal gets increased over a period of time. And this results in various problems. So for birds, one of the big issues was that the egg shells of many birds including eagles, pelicans and so on, so they started to become extremely weaker and crumble. And therefore the eggs were never hatching. So this resulted in a lot of issues, and by 1960s people started to realize that use of DDT has to be avoided somehow. So there was a big protest against the production and use of DDT. Therefore by 1972 DDT was banned from agricultural applications in US, and in 1973 the government approved that this decision is good, and from 1973 onwards in the United States of America DDT is not being used. However, they continued to produce it until 1986. They were producing DDT and selling it to other countries, and countries including India are still using DDT, and right now India is the only country that produces DDT. So even China has stopped producing it now, but India still produces DDT. The harmful effects of DDT are known, but still it is a sad thing that we are using it because it is an effective insecticide. So any other replacement of DDT with other compounds are expensive, so that is one of the reasons why DDT is continuing to be used, but this is something that has to be avoided if possible. So in short, whenever we talk about polyhalogen compounds, DDT is something that we cannot ignore. So that is a polyhalogen compound that had a lot of application which people stopped to apply, and now we have to reach a phase where we stop using DDT completely. So this is all about this particular unit. So in this unit we have discussed the reactions of haloalkanes and haloarenes in detail. And you would know that the various topics that we covered, so we started off this unit by discussing about some very much biologically active compounds that fall into this category. At that time itself I have told you that polyhalogen compounds are harmful. So we have now seen some of the examples, and you know, despite having certain applications, they are still harmful, so they have to be used with care. Then we went ahead and we discussed about the classifications of haloalkanes and haloarenes. The simplest classification was as monohalogenated or polyhalogenated compounds and so on. Then we discussed about the methods of preparing them. Alkyl halides or haloalkanes are prepared largely from the alcohols by using either HCl, or you can use phosphorus trihalides or phosphorus oxychloride. And the best method to make chlorides, chloroalkynes from alkyl halides, is by using thionyl chloride. So, because the byproducts that was formed are gaseous. Haloalkanes are prepared mostly by using electrophilic aromatic substitution and also by way of Sandmeyer reaction, which we have seen. While most of the synthesis of these compounds would rely on the synthesis of chlorinated and brominated compounds, fluorinated and iodinated compounds or fluoro and iodo organo compounds are generally prepared by doing halogen exchange. Then we went ahead and talked about the properties of these molecules, their physical properties. They generally have higher boiling points than their hydrocarbons. They are dense. Most of the polyhalogenated compounds are denser than water, however their solubility in water is very less. So these are the main points that we discussed. Then coming to the chemical properties or reactivities of alkyl halides. Alkyl halides have three major reactions. The most important one is nucleophilic substitution reactions. Then the second one is elimination reactions of haloalkanes, which gives you alkenes. And finally the reaction of haloalkanes with metals, where Grignard reagent was one of the very useful reagent that we could prepare by making a carbon magnesium bond. So we talked about that, and you in later units you would see that Grignard reagent is used in organic synthesis for making very many number of compounds. And in the reactions of haloarenes, which we discussed today, we said that nucleophilic substitution reactions are possible but under harsh conditions, but electrophilic substitution reactions of haloarenes are the most commonly discussed one. Haloarenes do not have an elimination reaction in general, because an elimination would require that you put a triple bond in an aromatic ring. So haloarenes do not give you elimination reaction except for under very special conditions. And they also do react with metals, where but most of the reactions that they can also form Grignard reagents with metal when they are treated with magnesium, but we mostly discuss the Fittig reaction and Wurtz-Fittig reaction in this. And finally we talked about polyhalogen compounds, and we discussed a number of their applications, but we emphasized on the fact that polyhalogenated compounds cannot be used in larger amounts, and as much as possible their application has to be replaced with certain other compounds, because they might continue to be in the environment and cause harm to the living organisms. So that is the end of this unit. Thank you very much.